Okay, so today we're going to go back and we're going to talk for a while about hypercontractivity related things. We talked about this many lectures ago, maybe lecture 12, and we saw this very easy Binomial lemma, which was about reasonable random variables. And in particular, it said that low degree functions of random bits are reasonable. So their fourth moment is bounded by something like 9 to the k times the square of their second moment. Or you might write it like this in terms of norms. And this was a great lemma. It had like a very, very easy inductive proof, induction on n. And you can get a lot of mileage out of it. In fact, I'm not sure we're going to do much of anything in this class that really needs any more hypercontractivity than it. But for culture's sake, we're going to tell you more anyway. There's also a very related theorem. They look kind of similar. The 2-4 hypercontractivity theorem, which says that if you take a function f and you smooth it out a little by applying t with parameter 1 over root 3, then that thing's 4 norm is bounded by its 2 norm. And there's a similar, very easy inductive proof of this by n. And these things are kind of equivalent. From this one, you can easily derive this one in a black box fashion. And the same is true in the other direction if you apply enough tricks. But they're kind of similar. OK, and we already got a lot of great conclusions out of this theorem. So one thing we did was we, given this, some like simple trick using Holder inequality gave us a similar looking statement, which was that you also have t1 over root 3 f 2 norm is at most f in the 4/3 norm. Okay, so it's another way of quantifying the fact that this is a smoothing operator. Once you apply it to something, even a big norm is smaller than a smaller norm. And if you square this, then these are even equivalent. This thing becomes the noise stability of f at parameter 1/3. Okay, so then you get like some nice combinatorial results, like if, so this all implies if f is a function into, let's say, 0, 1, and the expectation of f is alpha, so it's the indicator of a small set, then the stability at 1/3 of f is at most alpha to 3/2, which is very small. So somehow small subsets of the cube have really high noise sensitivity. And from this fact, we like to derive KKL, and we got all sorts of great stuff out of this Binomial lemma. OK, so that said, let's try to do a little more. So this looks a little fishy, not fishy, but like there's something like kind of weirdly specific about the fact that you have like 4 here, 4, and these numbers like root 3. I mean, it's quite natural to ask, like, I don't know, if you look at this one and say, OK, I suppose I have a degree k function. You know, is the 5 norm bounded in terms of the 2 norm, or the 6 norm, or the, I don't know, 2.5 norm, or what have you? And you know, it's a natural question. It's also not just an idle question because you know, you could analogously ask about how these parameters all trade off. And you might really want to do that because this is one of the corollaries. And you see this gives us a corollary about sort of the, you know, the noisy hypercube where the noise rate is 1/3. And that's like a very specific number. You might also want to know if like the noisy hypercube with other noise rates is a small set expander. It is, as we'll see. And there's nothing especially special about 1/3. But it arose all because it's particularly easy to do this proof for the 4 norm because, well, you'll see in a second that things are very easy when you look at the 4 norm. OK, so we'll get to that in a second. Yeah, we thought about this lemma in the context of trying to quantify the idea that random variables be reasonable. And one way we quantified this was saying that, you know, their fourth moment was not too much bigger than the square of their second moment. And one thing that's slightly annoying about that definition was that it wasn't closed under translation. So if you took a random variable that was reasonable and added a constant, it was no longer necessarily reasonable, which is a little weird. It means the definition is not incredibly natural. So to remind you, this is our definition of being B reasonable. Your fourth moment is at most B times the square of your second moment. And let me write this in terms of norms of the random variable. So I'll take the fourth root, and that's equivalent to this. And then let me bring this b to the 1/4 to the other side and also stick it on the inside, which is fine because this is a norm. So this is equivalent to saying b to minus 1/4 x. The fourth norm is at most the 2 norm of x. Okay, when you write it like that, it looks a little similar to this, this one. It's like you have this random variable, and then you're sort of saying if you smooth it by, multiplying it by this kind of small constant, then you actually get it to be smaller than its 2 norm. Okay, so back to the idea that it's not translation invariant. Let's try to fix that by introducing a new definition. So the new definition, it looks a little weird. That's why I've been talking it up as an idea of sort of fixing this notion to make a translation invariant. So we're kind of going to do that just by almost forcing it into the definition. So here's a definition that will be important. A real random variable x is said to be, for now, let's say 2, 4, rho hypercontractive if, well, it's like this, only we're going to sort of add a constant. So if a plus rho x to the 4th is at most a plus x in 2 norm for all real translations R. Okay, so this is some kind of definition. The downside of this definition is, as we'll see, is that it's sometimes kind of hard to check, even for a simple random variable, whether or not this is true, because you have to check some condition for all a. But if you manage to do that, then you kind of get more power out of it. And notice that it implies the random variable is reasonable with b equal rho to negative 4th or something by selecting a to be 0. Okay, so it's kind of a stronger definition. And more generally, we say it's p, q, rho. Sorry that p's look like rows. Hypercontractive if a plus rho x q is at most a plus xp. Okay. That said, we're pretty much only ever going to care about this definition when either p is 2 or q is 2, much like here. Sort of mostly only care when one of them is a 2. Okay, so let me make some small comments about this. First of all, this definition is scale invariant, in the sense that, if you take a random variable and multiply it by a constant, it doesn't change whether or not it's hypercontractive. Okay, that's for all non-zero C. Okay, and that's easy to see because you have this for all a in here. So if you multiply, let me kind of try to illustrate it down here. If you were to multiply x by c, so you got like a c up here, then you can divide both left and right-hand side by c. That doesn't change anything. And then this is a norm, so you can push the c inside, the 1 over c inside. And so you'd get like a over c, and then you would like cancel back out the c's. Okay, so since a over c ranges through the reals, when a ranges through the reals, it's equivalent. Does that make sense? Any question? Okay, so on that note, given that, you can also kind of see that the definition of, p, q, rho, hypercontractivity is also equivalent to saying that like a plus rho bx q norm is at most a plus bx p norm for all a and b in the reals. Okay, this looks like a stronger constraint because you have to satisfy for both a and b. Well, you can kind of see by the scale invariance or homogeneity that I can make an equivalent condition by dividing out by b, and that will cancel these b's, and I'll just get the ratio a over b. So in fact, by the same whole thing, I could also, in this definition, fix A to be 1. This was like this thing when B was fixed to be 1. So it's also equivalent to this. Okay, so I'll use whichever of the three equivalent things suits my needs later. Okay, one more thing. This is very trivial. I'll leave it to you to check that if x is hypercontractive with some parameter rho, think of p and q as fixed, then it's also the same with the same p and q, hypercontractive for any smaller rho. Which kind of makes some intuitive sense. I mean, if you make rho even smaller, it's like you're, squishing this random variable, like killing it even more. So it should only help you prove that the big norm is smaller than the small norm. Okay. Any questions? Okay, so what's the idea behind this? As I mentioned, this definition, it implies reasonableness, but it's actually kind of harder to check that even a simple random variable satisfies it. But the convenient thing is once you do make that check, then these hypercontractive random variables have like lots of great properties. For example, if you take a bunch of independent hypercontractive random variables and you add them, the resulting thing is, again, hypercontractive with the exact same parameters. Okay, and that's not something that's true of B reasonable random variables, which is, again, a little annoying. You kind of feel if you add up a bunch of random variables that are reasonable, the result should also be equally reasonable. And so this definition really facilitates like proof by induction, and it helps us reduce the general n case to like the n equals 1 case for all these statements. Okay, so once you make this clever definition and manage to show that, let's say, a random bit is hypercontractive, then all of these statements that you make in the future generalize easily to like understanding collections of independent random variables. Okay, so maybe I shouldn't have erased just that. Well, anyway, okay, so on that note, like let's think about our simplest possible random variable, a random bit. So let x1 be a uniformly random bit. Can we say that x1 is 2 for rho hypercontractive for, let's see, what value of rho? Kind of close. 1 over square root 3. This is, by the way, should range in the range 0 to 1. For rho, let's say equal to 1 over root 3, or even anything less than 1 over root 3. Okay, and that was because of, well, in fact, let's see the proof. One way to look at it is we need to show that by this, we need to show that A plus rho B, let's say x1, fourth norm, is at most A plus B x1, second norm, for all A and B real. And what I'm saying, I would like to point out, is that this thing, that's a terrible brace. You can think of it as f of x for f, a function, a 1-bit Boolean function, whose Fourier expansion, if you will, is A plus B x1. Okay. For all real A and B, I can define this. It's kind of degenerate, but real value Boolean function on 1 bit. And then this statement is exactly saying that f, sorry, that was terrible. This thing is f of x. And if this thing is f of x, then this thing is t rho f of x, right? Because how does t rho act on the Fourier expansion? You just multiply all the degree k stuff by rho to the k. Well, there's only one thing with degree 1. It gets multiplied by rho. So this whole expression, or this inequality, is equivalent to t rho f fourth norm is at most f the second norm. And this was this thing that we proved as a consequence of Binomial lemma. This is what we called 2-4 hypercontractivity. Okay, we actually proved this for all functions, even of n bits, but we'll just apply it for n equals 1 and get that this is true when x is a random bit. Sorry, this is true for rho, let's say, equal to 1 over root 3. Does that make sense? OK, good. So great. So we managed to show that if you have a very simple random variable, x1, it's 2-4 hypercontractive with rho equal to 1 over root 3. And that's the best possible rho, the largest possible rho for which it's true. So as I said, let's try again. Let's try another norm. And as we'll see in 1 second, that the second easiest norm to try this definition out on is the 6th norm. And then the third easiest is the 8 norm and the 10 norm and so forth. In other words, the easy cases are when this q is an even integer. And you'll see why that is in 1 second. So let's ask another question. Let's say if x1 is a bit, as always, a random bit, can we show that it's 2-6 rho hypercontractive for some rho? Okay. Since the 6 norm is always bigger than the 4 norm of a random variable, you're probably going to have to take a smaller rho. You're going to have to kind of crush the bit even more in order to make its 6 norm smaller than its 2 norm. OK, well, how would we try to prove this? Well, let's look at what we need to prove. For this, I'm going to use this equivalent definition. OK, so we need also something terrible is going to happen because my lowercase b's just look like my my 6's. So we'll be very confused. So we need 1 plus rho b x1 6 norm at most 1 plus b x1 2 norm for all real b. I guess my 1s also look like parts of my norm signs too. OK, so we're trying to sort of remind you here, we're trying to identify a rho, hopefully as large as possible, such that this is true for every b. OK, so it looks like a bit technical, but it'll be good to do it. OK, and why did we select 6? It's because we could equivalently raise this thing to the 6th power. And then this is very nice because this thing, the left-hand side, is the expected value of 1 plus rho bx1 to the 6th. OK, and the great thing here is we do not normally, if you have the q norm, you have to put absolute values in here. OK, because this thing could be positive or negative, so you can't raise it to some real power unless you first stick in an absolute value. But luckily, if this thing is an even integer, then you can just put in nice round brackets. So it's fine even if it's negative, and that's good because then you can literally expand this out, which is what we're going to do. OK, so if it was 4.5 up here, or even if it was an odd number like 5, you would have some suffering due to the brackets, to the absolute values. OK, and this 6 I'll just turn into a 2 times 3. So this is the expected value of 1 plus bx1 squared. Also convenient that 2 is an even integer, cubed. OK, well, we're just going to muscle it out now. So this one is easy, well, relatively easy. well, where should I write this? Let me write it over here. Okay, on the right-hand side, we have the expected value of the square of something. If you want, you can view it as like a little function on one bit, x1, and use Parseval to deduce that it's 1 squared plus b squared. Or you could just do it out. So the right-hand side here is 1 plus b squared cubed, which is, I guess, 1 plus 3b squared plus 3b fourth plus b sixth. Okay, see, that's an example of some terrible orthography. Okay, so what about the left-hand side? Let me do it here. Well, let me do it here. Okay, so the left-hand side. Okay, so I'm going to go do it all in sort of one step. So I'm going to mentally expand this out, like by multiplying out 6 things, and also take the expectation at the same time. Okay, so the first thing is 1 to the power of 6, so I get a 1. And then I'll get like 6 times the expected value of rho b x1, which is 0. Okay, so sorry, note takers, I'm just going to erase that. Okay, so the next thing is 6 choose 2, expected value of rho squared b squared x1 squared, which is, well, it's too easy, I guess. x1 squared is just always 1, in fact. So this is just 6 choose 2 times rho squared b squared. This is also known as 15, I guess. Okay, then we're going to get like 6 choose 3 times expected value of rho cubed b cubed x1 cubed. But expected value of x1 cubed is 0. So I'm going to erase it. And then the next term we'll get 6 choose 4. Take my word for it, you'll get rho to the 4th. B to the 4th, because you also get expected value of x and 1 to the 4th, which is 1. This is also 15. And then the 5th term will become 0, because the 5th moment of x1 is 0. And the last thing will be just rho to the 6th, b to the 6th. OK. Great. So we want the left-hand side to be at most the right-hand side, and it should hold for all b. Well, this is going to happen. Imagine take b to 0. Okay, it holds for all b. It should hold sort of in the limit. Now the b to the 4th, b to the 6th is kind of going to be negligible compared to the b squared. Okay, so you could see that you better just have this first piece less than or equal to this piece here for all b. And so it's clear, therefore, that actually you're going to need 6 choose 2 rho squared less than or equal to 3. Okay, so that's 15 rho squared less than or equal to 1/5, rho less than or equal to 1 over root 5. So that it shows that it's necessary that rho be less than or equal to 1 over root 5. But then it's also sufficient, right? Because here you have like 15 over root 5 to the 4th, which is going to be smaller than 3, because it was smaller than 3 even when it was squared. And like here you'll have 1 over root 5 to the 6th, which is way smaller than 1. So term by term, it's OK. So it's OK, even term by term. You know, if and only if rho is at most 1 over root 5. OK, so we've shown that a bit, you know, for rho equal 1 over root 5, which is smaller than 1 over root 3 as expected. OK. So, if we're just going to keep going, you might say, what about 8? That's the next one. We could say, what about 8? Well, I could do something similar, right? I just have like an 8 here, and I have a 4 up here. Okay, so in the 8 case, you see my right-hand side will start out, it's going to be 1 plus b squared to the 4th. So it'll start out as like 1 plus 4b squared plus some more things. And the left-hand side will be, well, expected value of 1 plus rho b x1 to the 8th. So looking at this thing, you'll see it's going to be something like 1 plus, and you'll get like 8 choose 2, rho squared b squared plus, 8 choose 4, some other stuff. That's going to have a b to the 4th. Okay, and you can see again, by taking b to 0, you see you're going to need to have this coefficient, at most this coefficient. So you're going to need 8 choose 2, rho squared at most 4. That's 8 times 7 over 2. Rho squared is at most 4. So these things cancel, and you get the rho at most 1 over root 7. Okay? That doesn't show, we didn't finish the calculation. That doesn't show that it suffices to take rho at most 1 over root 7. It does show that that's the best you could possibly take it to be. Okay, if you worked hard, if you finished it, you would show that it actually suffices. And in fact, I guess you could do this for all. You see the pattern now, I assume. You could do this for all even integers. And you would probably decide to yourself, or indeed prove, the following theorem. Let me just write x is a uniform random bit. And for all even integers q greater than or equal to 2, x is 2, q. You see the pattern. It's 1 over root q minus 1 hypercontractive. If you prove that, that's good. It would tell you, for example, if you went through all those corollaries, like something about small set expansion in the noisy hypercube Markov chain where this is the noise parameter, but we'd still ideally like to have it for all q. Like we'd kind of like to guess or perhaps cross this out. I should have not crossed out the for all. We may hope that this is true. And this is true. Okay, so we will prove this. Great. So this is kind of let me call this the Q theorem for the purposes of today. Okay, so this is something that we'd like to have true. In fact, once we get this to be true, then, as I'll show you, see, this is, as we said, this is literally equivalent to saying that, some bugs in here, t 1 over root q minus 1 f q norm is at most f 2 norm for all 1-bit functions f. Okay, right? Because a generic 1-bit function just looks like a plus, well, we know we could also stick a b in here, a plus bx. Okay, and then I will show you that like an easy induction will let you extend this to n, which is sort of the final hypercontractivity theorem that we want. Okay, any questions so far? All right. Good. So, yeah, so now it gets a bit of a drag because everything was going great, well, modulo having to deal with some binomial coefficients when q is an even integer. But if it's not an even integer, then you're kind of in trouble. Well, it's not exactly clear what to do. Okay? So now you have to rely on some slick tricks. So I will show you some slick tricks to prove this. Okay, so the main slick trick is, remember actually when we proved this with f equals n, kind of like the very first thing we did was like some very simple trick using Holder's inequality. We had 4 and 2 here, and we did some very simple Holder's inequality to get to get 2 and 4/3 here. Okay, maybe you don't remember, but it was a simple trick. You could do the same trick, and you'll get something that looks like this. Root p minus 1 f 2 is at most f p. And this would be for all p between 1 and 2. Okay? I'll, in fact, do that trick eventually, but if you were to do that trick, you'd get this sort of similar looking statement, except it's about norms that are between 1 and 2. So let me say the P theorem is that this holds if x is a bit. Okay, so I guess I would say this holds for all f minus 1, 1 to the 1 to r, i.e. a single bit x1 is p2 root p minus 1 hypercontractive. And the reason I bring it up is that this theorem has kind of a slick proof. So oddly enough, like this one has a slick proof, this one does not have a slick proof. So we're going to give this slick proof of this. And I told you this implies this. You can also, by some Holder trick, go backwards. Okay, so the way we're going to pull everything off is to give the slick proof of this and then use some like stupid Holder trick to get this guy. I may as well also say, in the interest of keeping you well informed, that here sort of tells you all about the hypercontractivity when one of the two quantities, p or q, is 2. There's a fully general theorem when they're arbitrary, and it says that t root p minus 1 over q minus 1, you probably guess it, f q is at most f p for all p less than q less than infinity. And we will not prove that because basically never need it. I've really never seen it used. But it's true, so. All right. So we're going to spend some time now proving this fact. OK, so let me imagine for a second that we're trying to prove this. And I'm going to do a few simple tricks at the beginning to I don't know, clear my throat and get rid of some annoying cases, and then we'll really start in on the proof. OK, so we got to prove this for all functions on the one-dimensional Boolean cube. So first I claim that without loss of generality, we can assume that this pathetic function f is non-negative. OK, so why is that without loss of generality? Well, basically, suppose we prove it for all non-negative f. Then for a general f, I'll take f and replace it with the absolute value of f, which is non-negative. OK, so then the theorem, by assumption, is true for this guy. I want to show that it's also true for the original guy. So I just want to show that, well, what happens when I do this? The right-hand side does not change when I make this replacement. Right? Because if you look at the p-norm of f, it's the same as the p-norm of the absolute value of f, because the p-norm has absolute value built right in. OK, so I just want to show that the left-hand side can only go up. And let me not waste too much time on that, but The left-hand side is t, some rho. I guess it's root. Let me just write rho. It's root p minus 1. How shall I write this? 2. We're trying to show that this is at most t rho absolute value of f, 2. And you see, this is actually equal to, this is going to be some crazy lines here, the 2 norm of the absolute value of t rho f. And I claim that this is true because I claim that t rho f is less than or equal to t rho absolute value of f pointwise. Okay, these are both non-negative functions, this thing and this thing. If one of them is less than the other one pointwise, then the norms are also going in the same direction. And this is because at a point x, this is like the expected value, absolute value of the expected value of f of y, where y is some noisy version of x. And this thing is the expected value of absolute value of f of y, where y is the same noisy version of x. Okay, so this is less than or equal to this by triangle inequality. Okay, I'll let you stare at that briefly if you don't believe it while I erase the next board, but it's just a, as I said, kind of a boring little trick to let us get rid of a few cases that are annoying to deal with. Okay, so, all right, great. We still got to prove this. Next, I'll say without loss of generality, you can assume, okay, so since f is non-negative, its mean is some non-negative number. If f is a 0 function, then we're done. So we can assume the mean of f is a positive number. And now I claim by scaling, I can assume that the expected value of f is 1. Okay, this is by homogeneity. Okay, if I'm trying to prove this inequality, it's preserved if I multiply by a positive constant. So I can arrange for the mean of f to be 1. Okay, so finally we know, remember, f is still all along just like a 1-bit function. So we know that f, its Fourier expansion, to dignify it with that name, is 1, because now its mean is 1, plus some coefficient times x, 1. So I'm just going to call this epsilon. And what do we know about epsilon? Well, we already know that f is non-negative. So f takes on 2 values, 1 plus epsilon and 1 minus epsilon. So we know that, therefore, the absolute value of epsilon is at most 1. Okay? So I've just reduced to the case where the function is this thing, and this coefficient is at most 1. And now in the never-ending chain of these things, we're going to also assume that, in fact, epsilon is strictly less than 1. We can do this because if we get it for epsilon all epsilon less than 1, then we can get it for epsilon equal to plus or minus 1 by continuity. Okay, so now we got rid of like a bunch of annoying cases, and now we're going to start. Any questions? Okay, cool. All right, so let's remind ourselves what we need. Well, we're trying to prove this. So we need that, well, what is t root p minus 1 of this little function? It's 1 plus root p minus 1 epsilon x1, 2 norm, should be at most 1 plus epsilon x1 in p norm. And I'm going to raise this to the power of p. Okay, so this is our goal. let me just tack on here for all epsilon at most 1. And also for all p between 1 and 2. All right. Great. So let me call this star. And let's start with the left-hand side of star. It's this thing. We see you have a 2 norm in there, which is very nice. We're always happy about 2 norms because 2 is an even integer. We see that this is the expected value of 1 plus root p minus 1 epsilon x1 squared to the power of a half to the power of p, so that's to the power of p over 2. And this inner expectation, this is just an expectation over x1. We can do this. It's just the sum of the squares of the coefficients, so it's 1 plus p minus 1 epsilon squared to the p over 2. And I'm going to handle it just by some very simple inequality, similar to I don't know, the Bernoulli inequality. I claim that the left-hand side, therefore, is at most 1 plus, I'm just going to bring the exponent down and multiply it. 1 plus p over 2 times p minus 1 epsilon squared. And the justification of this is that, let me copy it down, 1 plus t to the r is at most 1 plus rt for t non-negative and r between 0 and 1. Okay, notice that our r here is p over 2. P is between 1 and 2, so this r is actually between half and 1. And this is some trivial inequality that you could prove using high school calculus. Okay, any questions about this so far? So the trickier thing will be dealing with the right-hand side. Okay, so what are we going to do about the right-hand side? Okay, the right-hand side of this thing. Well, we have the pth power of the pth norm, so it's just the expected value of the thing on the inside raised to the power of p. Well, absolute value. Let me write it. Okay. Well, it's absolute value of but now I claim I'm just going to curl these absolute values into parentheses. So why can I do that? Yeah, this thing is always non-negative because x1 is plus or minus 1. This epsilon is at most 1 in absolute value. So it's a non-negative function, so it's OK for me to write parentheses instead of absolute values. So let me just literally write it out. Half the time it's plus, and half the time it's minus. Okay, so good. So how am I going to handle this? I'm going to use the generalized binomial theorem, or Newton's generalized binomial theorem, sometimes it's called. And that's OK. I'm going to start doing a series expansion for these things. And that's OK because epsilon is strictly less than 1. Okay, so the condition for this series to be valid is that this thing in absolute value should be at most 1 in absolute value. Okay, so I'm going to have some convergent series for both of these things. And it'll be what's that thing? absolutely convergent, so you can even rearrange the terms if you want, which we will. OK, so here it is. So let me do this one. Half 1 plus epsilon to the p, so it's like 1 plus p epsilon plus, p choose 2, if you will. Although p is like a real number here. So instead of p choose 2, you write like p minus 1 over 2, epsilon squared. I'm going to run out of room. Next one is p minus 1, p minus 2 over 2 factorial, 3 factorial, epsilon cubed plus, OK, you see what I'm going to write here, p minus 3 over 4 factorial epsilon squared plus dot, dot, dot. OK, so that's the series. OK, and then I have a similar thing, but just with negative epsilon. So replace epsilon by minus epsilon 1 minus p epsilon. This will still be plus. And then this will be minus. This will be plus. OK, and you see that we're just averaging these two series. And when we do that, all the odd powers of epsilon will cancel. OK, so in fact, the right-hand side is literally equal to we get all the even terms. So 1 plus p minus 1 over 2 epsilon squared plus p minus 1, p minus 2, p minus 3 over 4 factorial epsilon to the 4th plus, I'm out of room. What's this? This is like the Pockhammer symbol, right? Who knows what in combinatorics what I should write? Yeah, OK. I'll write p choose. Well, no, I don't want to, though. All right, I'm going to write it like this. P, you'll see why I don't want to in a second. P minus 5. There, I fit it.
I think you write the number of things on the bottom right.
Sorry?
I think you write the number of things you're going to take on the bottom right.
Like P6 or something? Yeah. But then I think like Knuth has like something that's like this, which is actually kind of nicer. Because, maybe you have like P6. Because there's also like the rising factorial. I don't know.
What's wrong with p choose 6?
I would prefer to write it like this for this glorious next move that I'm going to make. Because we're almost done the proof. So you'll appreciate this notation in a second. Great. So we're trying to show that the left-hand side is at most the right-hand side, right? So we're like, great. 1 is less than or equal to 1. This is the same. So it suffices to show that these things are all non-negative. OK, so can somebody tell me why they're all non-negative? Sorry? Yeah, they're all non-negative because, yes, because p is between 1 and 2. So you see, this is positive and positive, so that's, well, non-negative. This is negative and negative, so these guys, their product is positive. OK, and you see, like in each of these terms, the first two things are both positive, and then the next bunch of pairs are all negative. Oops. That notation makes no sense, but did you get it? Like, yeah. OK, so then, I don't know, maybe it's obvious to you that if p is between 1 and 2, that p choose 6 is non-negative, but if you, yeah? I don't know. If you write it like this, then it's obvious. Yeah?
Does it also work for p between 3 and 4?
The one thing that we used, the other thing that we used was this. That's a good point, but we used p between 1 and 2 here as well, and that doesn't work. Yeah. OK, so this is somehow like a slickly done version of that thing we were doing originally with 6 and 8 on binomial coefficients, but some slick version of it that works out nicely. That's the end of the proof. OK. Any questions? Any more questions? This is a very mathy day, but it's the math course, so it's OK. So we did the P theorem. And now I would like to see, this was really my real goal in some ways, this Q theorem. So I will now like to deduce the Q theorem from the P theorem with some stupid Holder trick. As far as I can tell, you need a different stupid Holder trick than the one we used to go from the Q theorem to the P theorem. Well, I guess one learns these tricks after a while. OK, so now I know that this hypercontractive inequality holds for all 1-bit functions f. I want to show that that one also holds for all functions f. And this is for all p. I wanted to show this one for all q. Basically, to derive the one here with a given q, I use this theorem with p equal to q prime, like the Holder conjugate of q. OK, so here's a little proposition. This is the stupid trick. Suppose that you knew suppose you knew that T F suppose you knew that TF in the 2 norm is at most F in the P norm for all F, where T is a self-adjoint operator. Okay, so actually this is a general theorem about operators on space. Okay, and this is a self-adjoint operator. If you remember, that means that TGH equals GTH for all G and H. It's like it's a symmetric matrix. And it's true because the noise distribution is symmetric in x and y. We used this the last time we did a stupid Holder trick. Then T G, what shall I write here? P prime is at most G2 for all G. OK, and this is once you do the definitions, that's what we want. OK, so here's the proof. We're trying to bound T, G in the P prime norm. Sorry, where this is P prime is such that 1 over P plus 1 over P prime equals 1. OK, so here's a fact that you may know if you've taken some higher analysis classes. The P prime norm of a function is equal to the supremum over all functions f that have P norm equal to 1 of the inner product of f and the function. This is like saying that the dual space of LP is LP prime. Or, if you don't like such fancy language, you see this inequality, that this is at most this, is Holder's inequality. You see, because if I have this, I can say by Holder it's at most FP times TG P prime. That's Holder. This is at most this when P and P prime are conjugate. And in the supremum, I'm just assuming that's 1. So the fact that this is at most this for all f with this condition is Holder. And the fact that you have equality here is the fact that Holder's inequality can be tight. For any f, for any TG, there exists an f which makes Holder's inequality tight. And it's just like some power of this thing. OK. That's all I'm going to say about this. I always hate to use this trick if I don't have to, but I guess mathematicians like to do it. OK. So now we only have so many hypotheses, so we'll now use self-adjointness. So it's the sup over the same thing of TF, inner product with G. Now I use Cauchy-Schwarz. This is at most the sup over the same thing of the 2 norm of TF times the 2 norm of G. Wait, did something go wrong here? No, it's okay. And now I use this theorem that we have. Well, no, I use this hypothesis. By hypothesis, I can bound this guy. This is the sup over f of p norm 1 of the p norm of f times the 2 norm of g. Okay, and then this is all 1. So that's it. Okay. If anybody knows like a nicer way to deduce this, well, maybe this is nice, but that's the deduction. Let me know. Okay, so why, let me just do the parameters. Why do we get the Q theorem from the P theorem now? It's literally just checking the parameters. Let's see. Yeah. So the point is now that I guess we know that t root p minus 1 of, let's say, g in the p prime norm is at most the 2 norm of g for any g. Right, by this combination of these two facts. And now let's see if q is going to be, this is going to be q, p prime. P prime is 1 minus 1 over 1 minus p. Yeah. No, it's 1 over 1 minus 1 over p. Okay, so by this relation, so that's p minus 1 over p minus 1. Wait. I screwed this up when I was doing my notes, too. It's real simple. What's the right way to do this? Okay. Right. So this is equivalent. Let me replace p by p prime. So this is t root p prime minus 1 g p. I could call this q. All right, this is a mess. Okay. This is equivalent to this. I just wrote q equals p prime. That's it. And then I observe that p is like the prime of q. Whatever. Okay, so q prime is 1 over 1 minus 1 over q, which is 1 over q minus 1 over q, which is q over q minus 1. Okay, so q prime minus 1 is 1 over q minus 1. Okay, so this thing is 1 over root q minus 1. Okay, thank goodness. Okay. Great. So now we have both of these things. All right, so the last thing is what was kind of our goal all along, which is just to take this theorem and promote this 1 to an n. Okay? And this is really why we did all the suffering to show that not only was a bit, reasonable, but like it had this hypercontractive property because it facilitates this induction. Okay, so let's do it. So finally, and this is like essentially the main theorem of the day, from which you can derive a number of interesting consequences, like the fact that the noisy hypercube is a small set expander for any noise parameter. And you can get, remember this level 1 inequality that said a 0-1 function with small mean has very little weight at level 1. You can use what I'm about to show that it has very little weight on levels 1 through k. And you can get like a Chernoff bound for degree k polynomials of random bits, and lots of other delightful consequences that I'll show you next time. OK, so let's do it. we're going to prove the 2Q Hypercontractivity Theorem. Okay, this was originally proved by Bonami in her PhD thesis. And it's like this, but it's let f be a Boolean function on n bits into the reals. And for all q at least 2, t 1 over root q minus 1 f in the q norm is at most f in the 2 norm. Okay, so it's going to be by induction. It basically, again, the proof, if you manage to like hang in there through the notation, it sort of writes itself. There's like no step of ingenuity. It just works out. Okay, maybe the only step of ingenuity is to decide to prove the square of this. So we'll prove, I might just start writing t here. T f of q norm squared is at most with 2 norm of f squared by induction on n. Okay. Yeah, we have our choice of where to start the induction. We can start it at n equals 1, sorry, which is this theorem. So we're done. We can even start at n equals 0. And then why is it true if n is 0? Yeah, the only then a function on n bits is just a constant. So you really have like a constant squared is less than or equal to itself squared. So that is true. Okay, so the n equals 0 case is easy. All right, so let's do the general step. So for n at least 1, okay, we're going to do what we always do when we do these inductions. Okay, we're going to write f of x. Well, let me write it as f of x prime and xn, where this is n minus 1 bits. So I'm going to imagine focusing in on the last bit. And like we always do in these inductions, I'll write, this is a multilinear polynomial, so I'll break it up into the part that depends on xn. Okay, which in our notation, the part on xn is actually the derivative function with respect to n of f, and that's a function only of bits 1 through n minus 1, plus sometimes we wrote the expectation function of f. Okay, but if you don't remember that notation, it's just if you have a polynomial, there's the part that depends on x, you factor out and get a lower degree polynomial, plus the part that doesn't depend on xn. Okay, and in the interest of notation, I'm going to think of x prime as, well, and also xn as random variables, and I'm going to denote this whole random variable by lowercase d, which is a little bit weird, but lowercase d, it's a function of x prime, and I'll denote this guy by lowercase e. Okay, and I'm also going to denote, as I've noted here, I'll write t for t 1 over root q minus 1. And since we're going to be looking at t of f, we should observe that, well, I'll observe it over here. Okay, so we got the left-hand side to start with. Okay, so we have t of, xn times d plus e q norm squared. Okay, and this d and e are functions of x prime, and this q norm is really with respect to x prime and xn. Okay, so what is the action of t? Well, you get one factor of rho coming out. And then you get td, and then t is a linear operator, so you just get te here. Okay, you have to add in an extra 1 over root q minus 1 to account for this xn, which had been deleted from the derivative. All right. Great. So this is the expectation of this thing in absolute value to the q to the 2 over q. So I'm going to write the expectation in 2 steps. First, I'm going to take the expectation with respect to the n minus 1 first bits. That's x prime. And then I'll take the expectation with respect to the last bit, xn. And then I'm just going to write what I've written here. I'm going to switch them, though, the order. So te plus 1 over root q minus 1 times td times xn, absolute value, q, 2 over q. OK, so I just broken up the expectation into 2 things. This, in general, is the expectation of the function on the inside, absolute value to the q, to the 1 over q, and then I have a 2. OK, so now what I want you to notice is this. Say we've done the outside expectation. So we've chosen the first n minus 1 bits. OK, now d and e, the derivative, they're only functions of these first n minus 1 bits. OK, so having chosen them, these things, really, this is like a function of x prime, and this is like a function of x prime. They become numbers. OK, so on the inside, this becomes some number, which I may call a. And this thing becomes some number, which I may call b. That's a number, and that's the bit. OK, that's xn, a random bit. OK, so you see what's going on in here is this thing on the inside with this notation. This is like expected value over xn of a plus 1 over root q minus 1 times b times xn, absolute value to the q. Okay. And this we can apply the p theorem, the n equals 1 case to. Right? That's exactly the scenario. Okay, it's like a 1-bit function. Does everybody see that? Okay, so by induction, oh, that red is really impossible to read. Well, anyway, so by induction, okay, this is at most, well, the inside expectation is at most the qth power of the 2 norm of that inner function, right? A plus b xn 2th norm qth power, right? Which is, let me just say, I'll make that qth power 2 times q over 2. So this is the 2 norm squared of this tiny function of 1 bit. So we know that that's a squared plus b squared, the q over 2. OK, that's the main step. Good. So overall, then, this left-hand side, or what we're tracking, is at most, let's put it back into the big expectation. We get the expectation over x prime of, well, and remember, what were these a and b? It was just t d and te. So this is td squared plus te squared to the q over 2. Okay, and remember, this is really like, this is a function of x prime. This is a function of x prime. Okay? So what's going on here? We have the expected value of some stuff to the power of q over 2. All right? So that is like, oh, wait, I dropped something. I dropped this, which is good, because it's going to help me out just now. So even better, we have the expected value of some stuff to the power of q over 2, all to the reciprocal, 2 over q. So that's the q over 2 norm of some function, well, some quantity. So that's literally equal to td squared plus te squared q over 2, right? Deepak, this really reminds me of what's going on in your paper. Somehow you got a norm, but then like the squares are on the inside. Yeah. Okay, great. Can anybody suggest the next step? What are you going to do? You got the norm of the sum of two things. Yes, the triangle inequality. Is that a valid triangle inequality? Yes, because q is at least 2. Which is to say, when I wrote this norm, you know, q over 2, so you notice that q is at least 2 by hypothesis, so this is at least 1. So this really is a norm. Okay, it's not like the half norm or something. It's a norm, i.e. it satisfies the triangle inequality. Okay, so continuing, this is at most td squared q over 2 plus te squared q over 2. Now let's just continue messing around. Okay, what's the q over 2 norm something? It's the expected value of the thing on the inside to the q over 2. So that's a q to the 2 over q plus the expected value of te to the q to the 2 over q. Is that right? Yeah. Great. Then you say to yourself, oh, look, I have the expectation of like something to the q. So that's like a q norm. It's like the q norm of td. Well, the q norm would have 1 over q. So now I've got a square. Okay. Now can somebody make a suggestion? Yeah, actually, I made a lie. This is where we have not actually used the induction hypothesis. This was a mistake. This is by like the n equals 1 like side fact. It's kind of like it's by the base case. Now we're actually going to use induction. Yeah, let me say this is by the base case. Now we're going to use the induction, and we get that this is at most d 2 norms squared plus e 2 norms squared. Okay, and remember here is f. So f is like xn times d plus e. So actually this equals the 2 norm of f by Parseval squared. Okay. Questions about that?
Is there something true about the more general product distribution?
Yeah, we won't get to see that in this class, but basically, this induction really only used the base case. So suppose you had, suppose x1 through xn were not necessarily bits, but they were independent. We used independence. And they're, let's say, we use Parseval too, so let's assume also the expected value of xi squared is 1. Actually, that doesn't even really matter because it's homogeneous. So, and we just had that they're 2q rho hypercontractive, these single random variables. Then this statement also holds, like for any multilinear polynomial of them. Okay, if you take a multilinear polynomial applied to them and measure its 2 norm, And then you take the same multilinear polynomial applied to them, but you like multiply the degree k stuff by by rho to the k, and measure the Q norm of that. Then this inequality holds. Which is to say, basically, if f is a function on like a different product space than uniform distribution of plus or minus 1 to the n, this induction really didn't use that at all. So it suffices to analyze, to get something like this, it suffices to analyze the hypercontractivity of the single random variables, which can be some pain and suffering. For example, it took us like a noticeable amount of work even to analyze it for like a uniformly random bit. But we did it, and there are some theorems that can tell you about hypercontractivity of single random variables. OK, so I can take another question, but let me just make one more last deduction. OK, so finally we proved this. And now we can go back and get this theorem. It's kind of this crazy loop. You know, it was better to be on this side, 2q, to do the induction. And now if we want, we could go back to the other side. This is also proved by Bonami. Again, for any function, and for all 1 less than or equal to p less than or equal to 2, t root p minus 1 f 2 is at most f p. OK, so this we had for n equals 1. And now I'm telling you it's also true for general n. And you can get it by taking this and doing one more Holder trick. In fact, the Holder trick that we already did, see, we did this deduction from here to here in lecture 12 when q was 4, and this was 1 over root 3, and then we got this to be 1 over root 3 and 2 and 4/3. And it's literally the same trick, a different Holder trick. OK, and once you have this, you can take f to be the 0, 1 indicator of a, you can square, you can take f to be the 0, 1 indicator of a set. You can get a small set expansion theorem for the root p minus 1 noisy hypercube for any p of your choice. So that's one nice corollary. And we'll see some more corollaries of this stuff next time. Any questions?